Okay, this video is going to go through the ideal gas law. So the ideal gas law defines a relationship between all variables in gas problems. So this takes into account pressure, temperature, volume, and moles that we've been looking at in all of our gas laws so far. The difference between the ideal gas law and all of the other gas laws that we've looked at, say Boyle's, Charles, and Avogadro's, is we're not looking at an initial and a final condition. Rather, we're looking at how the gas is behaving at one snapshot in time. So before we actually get into the ideal gas law, I want to go through the three individual laws that we've looked at here and sort of look at how they can play together and how they actually are rearranged to figure out this ideal gas law. So if we look at Boyle's law, remember Boyle's law states that volume is inversely proportional to my pressure. Charles' law, we said volume is proportional to my temperature, and Avogadro's law looks at how volume is proportional to the number of moles. So I'm not really too concerned about deriving this gas law or really calculating the R value, but I do want to show you how we've done that and why all of these things are really interrelated concepts. So if I'm going to take a proportionality and convert it into some form of an equation, I need to add a constant into it. So if I look at this one, I could say that volume equals some sort of a constant, let's call that K, times this inverse pressure. If I rearrange this equation even further so that I isolate for K, K would equal P times V. So remember, we did look at this quickly back when we looked at Boyle's law, and we saw that if I set K1 equal to K2, really that's saying that P1 V1 equals P2 V2. So that's where the initial Boyle's law came out of. Same thing with Charles' law. I could set this as a equation. So I have volume equals this constant K again times T, or for Avogadro's, V equals this constant K times N. And again, both of these can also be converted so that I rearrange for solving for K. So I would have V over T, or for Avogadro's law, I would have V over N. So really, if I combine all of these together, notice that T and N are the bottom. I have this PV that's hanging out on top. So I could set all of these K values as my ideal gas law, and we're going to call this constant R. So we're just changing the letters to make things really exciting here. So if I rearrange and I have P, V over T and N, when I put it all together, rearrange that one, I can set this as PV equals NRT. And remember, we're saying that R value is really just the K. So looking at all these variables, PV, N, and T are all the same things. So I have pressure. Pressure for our ideal gas law, we are always going to measure in kilopascals. Reason being is where you're going to use the 101.3 kilopascals to calculate our R value. If you're going to use any other unit of pressure, you would of course have to recalculate that R value. V is for my volume. Volume we're still measuring in liters. N is for the amount, and this is going to be measured in moles. T is my temperature. Remember, all gas temperature things are measured in Kelvin, and R is my ideal gas constant. Okay, the ideal gas constant has real funky units, so we're going to go through how I can actually derive this ideal gas law and figure out what these units are that accompany it. Okay. So R is calculated using standard molar volume, which means that I'm looking at 1 mole of gas would occupy 22.4 liters at STP, so those standard conditions. So remember our STP values, my temperature would be 273 Kelvin, and my pressure would be 101.3 kilopascals. So if I look at this ideal gas law, I have PV equals nRT, If I'm rearranging to solve for my R, then I can divide both sides by NT. So really I have this R value equals PV over NT. And this rearrange really should help you out with the units when you're trying to solve for those. So let's calculate our R value now based on our standard molar volumes. So R equals PV over NT. We said this is 101.3 kilopascals is my pressure. My volume, as we said in this point here, is 22.4 liters. This is for 1 mole of a gas. And the temperature, again, is standard, so 273 degrees Kelvin. You'll notice here that none of my units are actually crossing out here. So my R value is actually going to have the unit kilopascal liters per mole Kelvin. So if I sub this in, I get the value 8.314 kilopascals liter per mole Kelvin. So this is the ideal gas law constant, and you do need to sort of commit this one to memory as we will be using it throughout today's work, as well as when we're looking at stoichiometry of gases.